Good evening, everyone, and welcome to tonight's CRAM session, Unit 2, Biological Psychology. So tonight is the whole presentation where we're going to go through, well, not every single possible concept, but a lot of the major concepts that are part of this unit. We're going to talk about some major themes, and then also to encourage questions, I have the question box thing activated. And if you have a question about something or you're not sure of something as we go through something, please use the question box to pose the question. And towards the end, I will go over it. I figure that's a much easier way of doing it so that the flow is not interrupted. So that's the plan. And lots of hellos in the chat. Good to see you all, if not only virtually, I should say. So if you're going to ask a question in the question box feature, make it specific so that I know when I go back to, oh, it's about this concept, and perhaps I can go back to the slide where it contains that. So I want to make sure that your questions are answered and things are clear. So with that, just some few plugs for upcoming things. Tomorrow is AP Psych Units 3 and 4 Trivia. 5:30 p.m. Eastern Time. That's tomorrow, Friday. And then next week, the 16th, April 16th at 3 p.m., I'll be doing question and answers about Unit 4. That says Sensation and Perception, but that's actually, it's learning. I forgot to change the text there. Unit 3, which is tonight, Unit 3 is Sensation and Perception. We did Q&A for Unit 3 earlier today. It's Unit 4 is next week, which is sensation. Unit 4, which is learning, Pavlov, operant conditioning, all that stuff. So that will be next week. And of course, our social media at Fiveable on Twitter, Instagram, and YouTube. So what we're going to look at here are essentially 5 major themes. And when I say 5 major themes, what I would call the 5 major parts of this particular unit, and they're not all independent of each other. There are interdependent of each other, that they do connect and have some variance in common. But the brain, neurons, and neurotransmitters, the nervous system, endocrine system, and sleep and dreams kind of make up this unit here. And we're not going exactly in the order that you see here, but nevertheless, that is the plan. I will also just give you a quick heads up that my 3-month-old son is in the other room sleeping right now, and he could wake up at any time, and I might have to run out real quickly to bring him to his mother, which I'm just letting you know ahead of time in case that should happen. If I need to, hopefully my wife will get to him first, but I just want to make sure that you know that I'm not just running away spontaneously. So with that, I want to jump into the first part here, which is going to be the neurons. Okay, so we're going to talk about neurons. We're going to talk about, and again, these slides will be available afterwards. Some of these are text heavy, some of these not so much, and I'm not going to read the text from these slides. You can do it at a different time right now, or they'll be available afterwards. You can look at them. So essentially, this is the neuron. It's the basic part of the nervous system. And it has, for our purposes, very few parts that you kind of need to know here. And I am using some material that's been used in the past. I'm not making that, so I'll be very clear about that. And the goal here, of course, is to let you interact and ask questions. So the cell body, which is kind of the nucleus, and within it, it holds what's called the soma. Some textbooks say the cell body is the nucleus. Some say it's the soma. But it's basically the brain of the neuron. It has, branching out from it, these little kind of tree-like fingers or something like that, these tree-like branches, which are called the dendrites. The dendrites are what receive the messages. They are what take in the messages and from previous neurons. In other words, previous neurons send out the messages using neurotransmitters to those dendrites, and when those dendrites get enough of the neurotransmitters, they fire right off. So that message goes down in a sort of neural impulse, and it's an electrical impulse that goes down the axon. Goes down the axon. Axon equals away. In other words, it's going away from the cell body towards the dendrites. It is coded by this fatty layer called the myelin sheath. The myelin sheath is literally a fatty layer that insulates the axon and enables faster transmission. The faster, or I should say the fatter the myelin sheath, the faster the transmission goes down the axon. So then the message, this electrical impulse goes at the end to these terminal branches and these terminal buttons, which have these vesicles that are filled with the chemicals, the neurotransmitters, which are going to release themselves into into the synaptic cleft, which will go to the next one. So let's see here. So then we move on to essentially this action potential that it's called. It's what basically fires off. It's what is when the neuron fires off. They call it the action potential. It fires off, boom, action potential. The chemical process to it is remarkably complicated. There's some physics involved, but there's a lot of chemistry involved. A very complicated reaction where you have sodium ions when it's not firing off on the outside of the axon, and and potassium on the inside. When it fires off, the sodium flows in, the potassium flows out in this kind of chain reaction. I don't think it gets much more complicated than that. And they get in these things. They talk about terms like depolarization, where okay, there's too much sodium inside, and now it has to. It's hyperpolarized, meaning there's way too much in, and now it has to repolarize later on and kind of reset itself. So it is something that this chemical reaction. It's pretty complicated, but nevertheless, that's the basic idea to it. So then, as it reaches to the terminal button, it's full of those vesicles, or has those vesicles that are full of the neurotransmitters. They are released into the synaptic cleft, which are going to bind to the receptor sites of the next neuron. Now, when neurotransmitters are released into the synaptic cleft, there's one of several things that will happen to those neurotransmitters. One, it will bind to a receptor site, and each neurotransmitter can only bind to a particular type of receptor site. For example, dopamine will only bind to dopamine receptor sites. Serotonin will only bind to serotonin receptor sites, and so forth. So it's like a lock and key mechanism that occurs. So it gets released. That's one possibility. Second possibility is that it floats out of synaptic cleft and it's broken down by enzymes and they become amino acids because they just float out and they don't stay there. A third possibility is that if it stays in that synaptic cleft long enough, it gets reabsorbed by the presynaptic neuron. In other words, the neuron that releases the neurotransmitters into the synaptic cleft. It reabsorbs them. We call that reuptake. Reuptake, it's like a Hoover vacuum cleaner. It just sucks back up the neurotransmitters. It's not quite like that, but that's the idea. So it's in the synaptic cleft, it binds, it floats out, or it gets reabsorbed through that process of reuptake. Okay, so there are different types of neurons, and here we get into features. Differences between afferent neurons and efferent neurons. And this is something where it could be an easy selection on the FRQ, describe how an afferent neuron plays a role in this situation. Well, first off, the way I like to think about it is afferent, A for afferent, A for arrive, E for efferent, E for exit. Afferent neurons go towards the central nervous system. They are sometimes referred to as sensory neurons because when I touch something, the message has to go towards my brain. And it goes in this direction towards the central nervous system, the spine, and the brain through these afferent neurons. It's arriving towards my central nervous system. Efferent neurons, on the other hand, are called motor neurons. Motor basically being a very fancy word meaning movement. That essentially means, I can move the body. So for me to wave my hand, I need to have these efferent neurons that will allow me to move. So it is essentially the basic idea to that. And there are some people who have different mnemonics on how to remember those things. And if it whichever works for you, go with it. Like I said, I do A for arrive, A for afferent, E for exit, E for efferent, because as the messages go away from my brain to move my hand, okay, that is what I would do. So again, like I said, there are many, many mnemonics in this chapter here, or in this unit, I should say. So just different possibilities here. But you might get a question, for example, Jamie is playing soccer. Describe how efferent neurons will help her play soccer. Well, that would say, okay, well, the efferent neurons will help her kick the ball or help her catch the ball if she's a goalie or something like that. So it's if you kind of know what they are, that should be pretty easy to apply on the AP exam. There are probably, over 100 known neurotransmitters here, some of them being hormones in the blood. And there are, again, there's a couple of more common ones that are here that, again, you take them or leave them in terms of helping you to remember. Acetylcholine helps with attention, helps with memory. It helps with movement. Or I should say, to be able to move the body, you need to have acetylcholine. Dopamine is also helps with movement. Dopamine, one way of differentiating dopamine from acetylcholine is that with acetylcholine, it allows me to move my body. Dopamine allows me to control the movements. It allows me to be more precise with my movements, to be able to go this way or that way. It requires dopamine. It's also sometimes referred to as the pleasure hormone. It gives us a feeling of euphoria if we have dopamine surging through our system. High levels of dopamine are associated with schizophrenia. It doesn't mean that people with schizophrenia have more euphoria or they have more movement per se, although there's some symptoms like certain types of catatonia where they might be moving, but or catatonic symptoms where they might be moving beyond their control. Low levels, on the other hand, are associated with Parkinson's disease. So that if what they find here is that the synapses of a person with Parkinson's, the synapses associated with dopamine a lot of them are destroyed, and so they just don't work very well. So too much dopamine is associated with schizophrenia, too little dopamine is associated with Parkinson's disease. So moving on to serotonin, there's a lot of things with serotonin: sleep, hunger, mood. There are a lot of different things there. This is why sometimes when a person is not sure if they're in a bad mood, if they're tired, or if they're hungry, or some combination thereof, it might be because the serotonin levels are off, and it might make one feel one or all two or all three things in that case. It is low levels of serotonin are associated with depression. There's a lot of controversy about this. We do know that it seems that when people with depression might have low levels of serotonin in the blood, and there's a lot of controversy about that. There are some who even say, you know what, that's not even accurate anymore. But nevertheless, it is associated with depression. It has been historically linked to depression in some way. Norepinephrine, or as I like to say to my students, norepinephrine, there's no speaking test on this, helps us a number of different things. It helps us with alertness, arousal, mood, and it also references these agonists, and I'll talk about that kind of briefly. The agonists are substances that mimic, that will mimic the neurotransmitter. So they're chemically similar to a neurotransmitter. And an antagonist is what is, it prevents the neuron from firing. It basically blocks the neurotransmitters from binding. So yes, they are antagonists, might be drugs or any substance that will block the neurotransmitter from binding to receptor sites are going to be antagonists. So for example, talking about norepinephrine, cocaine is known to sort of be an agonist in some areas of the brain for norepinephrine. And like I said, they're not going to quiz you on that per se, but just to kind of give you an idea of what norepinephrine is and how it could affect us. And because people might take cocaine because they might try to get a feeling of euphoria doing it. So GABA is referred to as an inhibitory neurotransmitter. It actually slows down the nervous system. It actually slows things down. It makes parts of the nervous system work not quite so much. And you might say, well, why would you do that? Well, because, for example, a person with generalized anxiety disorder, oversimplifying the disorder here quite a bit, might have in certain areas of the nervous system too much activity. And so they might need more GABA to slow down those areas of the nervous system. So Valium, for example, is an anti-anxiety drug, a benzodiazepine, that kind of acts like GABA and can slow down parts of those brain, or of that parts of that brain that might be causing anxiety. The mnemonic I like to talk about with my students is Fred Flintstone says, yabba yabba do. I say gabba gabba don't. Norepinephrine can be, some of these neurotransmitters, the question was, is norepinephrine excitatory? For our purposes, yes. For our purposes, we're going to assume that GABA is the only inhibitory neurotransmitter, although norepinephrine, dopamine, and a couple other ones can also be inhibitory in certain parts of the nervous system. However, in AP Psych, they tend to treat GABA as the inhibitory one and other ones as excitatory. Glutamate is another neurotransmitter. It's an excitatory one. It helps speed up the nervous system. Has a role in memory. We know that people might have, for example, a glutamate sensitivity, and they have to avoid, for example, monosodium glutamate, which is a seasoning or a flavoring that you can find in some foods. And if they ingest that, then there is too much glutamate or glutamate, similar chemicals to glutamate that can excite the nervous system too much. It could cause migraines in those with the glutamate sensitivity. It could cause seizures in very extreme cases. That's why some people have to avoid MSG, monosodium glutamate, because of the glutamate sensitivity. Okay, so that sums up, I don't want to say sums up, but that is a CRAM of neurotransmitters, the neurons. Like I said, could there be certain minor details that could appear in the AP exam? Perhaps so, but again, we're covering the major parts here. So we're now going to move on to the second part here, which is the brain. And here we're going to talk about different parts of the brain. We also talked a little bit about the nervous system, the sensory neurons versus the motor neurons. I don't have a slide for this, but for some reason that was missing, the difference between the sympathetic and the parasympathetic nervous system. I'll make sure I cover that as well before this presentation is over. The medulla is the first part of the brain we're going to talk about here today. So, and I know there's some questions in the chat. If you could put them in the question box, that way it'd be very easy for me to access later on. That would be helpful. So again, if you were joining us late, please put them in the question box that's there, and I will address them at the end of the presentation. It'll be the easiest way of doing it. So the medulla is at the base of the brain, connects the spinal cord to the brain, sometimes referred to as the medulla oblongata. But medulla works just fine. It is in charge of the most basic functions, heart rate, breathing, reflexes. It helps with that particular purpose, located in the back of the brain. So when people talk about sustaining a brain injury, oh my gosh, a person sustained a serious injury to the front of their head, how'd they survive? Well, damage to the front part of the brain or the middle part of the brain isn't as likely to be fatal as damage to the back of the brain, because that's where the most basic life functions are housed, in the back of the brain. That's where the medulla is. Will you be expected to know exactly where a part of the brain is? I doubt it, given that this is an FRQ. I doubt that they're going to put a brain thing on there and say, well, what part is this? I strongly doubt that. Make for an easier multiple choice question. So I think more of the functions of this would be more important here. So that's what I would say for that. But understand the functions and where they generally are. Are they in the back of the head? Are they front of the middle of the head? Or the brain, front of the brain? I think those are more important. The pons helps with sleep and arousal. I tend to think about sleeping by the pond, by the pons. That's a mnemonic that I and other psych teachers use as well. So pons helps with sleep and arousal. The reticular formation located right behind the pons, it assists the pons in the, again, attention, filtering out irrelevant stimuli. So, for example, if you are listening to me and you're also hearing other sounds, and there's all things you can see and feel, all sorts of sensory stimuli that are around you, your reticular formation helps you to filter out whatever is not important. So, if you're paying attention to me, I hope you are, and there's, let's say, perhaps be an aquarium not far from where I'm at right now, I'm not really focused on the aquarium because my reticular formation is filtering that out. People have asked me, how do you remember that? It's, again, these mnemonics work for me, not for others. The reticular formation in this case, I think about football. And here, and if you don't like football, then this won't be too terribly helpful, although it could apply to other sports too. So a quarterback who is in formation is not in his home stadium. He's in a different stadium, and there's lots of crowd noise. And that quarterback needs to filter out all that noise. So let's get into the reticular formation. It sounds silly, but that's the way I remember it. The cerebellum is the next part, moving into the midbrain here, or roughly, some say midbrain, some say hindbrain, but that, again, I don't think is terribly important for this particular AP exam. The cerebellum has a number of different important functions here. It helps with balance. It helps basically keep our balance. It helps with fine motor movements. To be able to touch my nose with my fingers like this is a fine motor movement. Writing with a pencil is a fine motor movement. Plucking the strings of a guitar is a fine motor movement. All those things are very precise things that are needed in order for me to do it. Those are fine motor movements. A gross motor movement might be just moving my arm like this in no real particular fashion or no real specific way. That would be a gross motor movement. It also helps with the procedural memory, how to do things, how to tie your shoes, how to play the piano, how to walk. All those things are going to be part of the cerebellum. My silly mnemonic is my good friend cerebellum is rather clumsy and has difficulty keeping her balance. So it's like I said, some people use it, some people don't. And again, there are other people who've come up that use these same mnemonics too. So my good friend cerebellum is a rather clumsy person. These are, again, easy things that could appear on the FRQ. How does the cerebellum affect this? If you remember what the cerebellum does, there you go. All right. The hippocampus helps with many types of explicit memory. Memory of facts, memories of things that have happened in the past. The hippocampus is this part of the brain that helps us store the memories. It's not where the memories are stored, but it's what helps store the memories in other parts of the brain. So the way that I and other teachers talk about this Camp Hippo, where memories are made. And I don't have this GIF up here because I don't have own the rights to it, but or I should say it's not. I can't use it on this platform here. It's these two hippos that are in love with each other, and their little hearts and whatnot. And there are Camp Hippos, a little sign that says Camp Hippo, where memories are made. Some people use it, some people don't. So that's the hippocampus. The amygdala helps us with emotions and emotional memory. So anything that has to do with emotions or emotional memory goes to the amygdala. I think about my friend Amy G. Dallow, a very emotional person, overreacts to things, it just very gets upset by things very easily. Sometimes the amygdala is referred to as the fast pathway of emotion, primitive types of emotions where it kind of just, I would say more for our purposes, let's put it this way. For general purposes, they would accept any type of emotion. Technically, or I should say there's more research to show that it's more of the so-called primitive emotions that help us with our survival, anger, fear, aggressiveness. are usually more associated with the amygdala. However, they would accept any real type of emotional memory would be associated with the amygdala. Things like love, for example, are considered to be a higher order emotion and might go to other parts of the brain, but still the amygdala is going to play a role with that. So for our purposes, I would definitely stick to just generally speaking emotions and emotional memory. So this is why, for example, when people start thinking about a time when they were happy or angry, they might start feeling happy and angry because well, it's going to the amygdala, and that's what's happening there. All right. The hypothalamus is a big one here. This one, it does a lot of different things here. It contains a lot of our survival functions, not the heart rate and breathing, that's the medulla, but it's also referred to as the 5Fs. And just by a show in the chat here real quickly, has your teacher taught you 4 or 5Fs? So sometimes the 4Fs, sometimes the 5Fs? I don't know if, so, okay. All right, so yeah, I know it's been, I've talked about it in the past. The 5Fs are this. They are feeding, so it has to do with hunger, the feelings of hunger and satiation. Fighting, aggression, the fight or flight response, and with it goes fleeing. So fleeing, fighting, the fight or flight response. Fahrenheit, our body temperature, our body's ability to maintain a certain temperature. And mating. You might say, well, mating doesn't begin with the letter F. Well, use your imagination. And if you really can't use your imagination, then the 5th F stands for fornication, in case you were wondering. But this is the 5 Fs. Sometimes they talk about the 4 Fs. They don't include Fahrenheit. But yeah, feeding our body's ability to feel hungry is regulated through the hypothalamus. The fight or flight response is regulated by the hypothalamus. Our body's temperature is regulated by the hypothalamus, and our body's reproductive drive is regulated by the hypothalamus as well. The fight or flight system is a sympathetic nervous system response, which also goes through the somatic nervous system. This is true. But yes, but the hypothalamus plays a major role in that. Again, a lot of these textbooks, for good reason, they separate them into different things. So, but they do interact with each other. They do interact quite a bit. And sympathetic and parasympathetic is a question I do want to answer. But again, put that in the question box, and I will address that at the end because that is a very important thing. So, all right. So yeah, sexual arousal we would say is part of mating. Yes, that whole concept of sexual arousal, the reproductive drive, all part of the mating aspect. The thalamus is what takes sensory information and relays it to other parts of the brain, with the exception of sense of smell. Smell is the one exception because it goes through a different pathway in the brain. So basically, if my eyes see something, it goes to my thalamus first. Thalamus says, okay, go to the occipital lobe. Or I hear sound, thalamus says, okay, go to the temporal lobe. Yes, all these slides will be available afterwards for you to review. So that's what the thalamus does. All right. The different cortices, kind of the outer layer of the cerebral cortex. The cerebrum being like the outer layer, and the different areas being the cerebral cortex. Different parts and what they do. The frontal lobe in the front makes sense here. Frontal lobe helps us with decision because your motor cortex is going to be found in the frontal lobe, towards the back of the frontal lobe, but still in the frontal lobe. And it helps with decision-making abilities, to our ability to make decisions. It deciding to what the best course of action is, weighing choices, thinking about the pros and cons of something, go through the frontal lobe. It's the last area of the brain, developmentally, it's the last area of the brain to actually develop. The temporal lobe, which is located kind of right by the ears, this kind of makes sense, helps us with sound processing. And I've said this before, and I'll say it again, these lobes do more than just this. It's a lot more complicated than that, but it sticks to the very basics here. The temporal lobe corresponds to hearing. Parietal lobe, on the other hand, is the sense of touch, has what's called the somatosensory cortex, which is there. Actually, I just realized I have each of these laid out here. So I just realized I'm not kind of skipping around here. So yeah, the parietal lobe helps with the sense of touch, located right about here approximately. Temporal lobe, right by the ears, helps with hearing. And the occipital lobe, which has whether it be God that made us or evolution or both or neither or whatever, has a sense of humor. The occipital lobe is located at the back of the brain, opposite where the eyes are. So my eyes see something, goes to the thalamus and says, okay, go to the back of the brain. Back of the brain is where it goes to. So that's what the occipital lobe does. It helps with the sense of sight. Temporal lobe, for our purposes, refers to hearing, sound processing. That's where the auditory cortex is located. So for the difference between a cortex and a lobe, for our purposes, basically it's the same thing for our purposes. For our purposes, it's the same thing. The difference between a cortex and a lobe, for our purposes, I would say, is kind of, I mean, if you want to think about it, it's like the cortex is more the outer layering, whereas the lobes can get more in depth, literally deeper into the brain, but they won't get that specific on the AP exam. They would not get that. They would not quiz you on that. So, all right. So now, looking at different parts of the lobes specifically, two other favorites that could appear on the AP exam, especially on FRQs, Broca's and Wernicke's area. Broca's area, now we're looking at the brain. This is the left side view. So I always forget the camera is, this is my left. This might look like your right, I'm not sure. But this is my left brain, so we're kind of looking at my left brain right here from the side. Broca's area, located in the frontal lobe. Sometimes, some textbooks say it's in the parietal lobe. But again, they wouldn't quiz you on that because it's kind of disputed. The Broca's area helps with language production. Some people say, oh, speech production. Not just speech, but any type of language production. The ability to speak, the ability to sing, the ability to write out language, the ability to converse in sign language, American Sign Language, for example. You need Broca's area in order to do that. On the other hand, Wernicke's area helps us with language comprehension. We are talking about Broca's and Wernicke's area. Broca's found in the, again, frontal lobe for our purposes, I would say, and Wernicke's area in the temporal lobe. Again, I doubt they would quiz you on that specifically, but nevertheless, those are the general areas. If you look at this picture of this brain right here, it seems that, well, Broca's is definitely towards the front and Wernicke's towards the back, but I strongly doubt they would give you a diagram of the brain on the FRQ. I just don't think so. I don't think locations will be asked because it is something that is so... For one thing, you can easily look it up, and that would just give you the answer right there, I think. And they don't want to give you questions that it's just easy to find the answer, and there it is, and I write it down. It's more about understanding how it applies. So, good question here from the chat. I'll answer this now about learning a language. It's everything. You have to understand that when it comes to speaking a language, we need to have both. First off, Broca's allows me to speak the words, but Wernicke's also allows me to speak the words in a way that's comprehensible. So, for example, if my Broca's area is working fine, but I have Wernicke's aphasia, I might have difficulty. Well, I'll speak just fine, but you might not understand what I'm saying because it makes no sense. Likewise, if you're talking to me and I have damage to Wernicke's area, I might have difficulty comprehending your language or whatever it is that you're trying to say to me. Also, when you learn a new language, there's the hippocampus plays a role. There's so many different things that play a role in learning a very complex task, such as learning a new language. So understand the difference between Broca's, which is language production, being able to speak the language, to express the language, and Wernicke's area, which allows you to understand the language and allows you to communicate in an understandable sort of way. So those, again, parts of the brain. Although not covered here, I'll address it real quickly. The layer of tissue that's connects the two brains is the corpus callosum. A person might have their corpus callosum severed to alleviate the symptoms of seizures, of usually epilepsy, for reasons that go beyond the scope of this course. What might happen, though, is that the right brain, left brain can't communicate with each other because of Broca's area is damaged there. So, or I should say, I'm sorry, because because the corpus callosum is severed. Although usually in everyday life they don't have deficits, they don't notice a problem, only under controlled conditions. So again, in terms of the hemispheres, I'll address that real quickly too. The problem with these hemispheric things is that it's way too overgeneralized. Language is usually contained in the left hemisphere for most people, not all people. There's exceptions to this. So language, logic, usually found in the left hemisphere. In the right hemisphere, on the other hand, music, creative expression. But then you get this idea about left brain and right brain thinkers, and it gets very, very misleading. So again, there's other questions I'm not immediately addressing in the chat. Please make sure you put them in the question box, and I'll be sure to address them towards the end. So, all right, moving on here, the endocrine system. The endocrine system here addresses specifically the hormonal parts of the body. These are chemicals that are found in the blood, although some parts of the endocrine system are also considered to be neurotransmitters. We're going to stick specifically to how they, in this instance, how they work as endocrine system parts. Some are just knowing parts, some are knowing the chemicals, the hormones that go along with it. So to begin with, we have the pituitary gland, which is this area of it's a very small thing, looks like a pea. It helps with our growth. It's sometimes referred to as the growth part of the endocrine system. It releases hormones to help us grow. It also is considered to be the master gland in so much as it controls the rest of the endocrine system. The pituitary gland is actually controlled by the hypothalamus, and then the pituitary gland basically communicates, loosely I say that, to other parts of the endocrine system. Okay, thyroid, do this, pancreas, do that. So that's the pituitary gland. And I also like to throw a picture of Andre the Giant. He was a professional wrestler. You might know him better as the character in Princess Bride. He had an overactive pituitary gland that made him be very, very tall, very big, which made him very large. But the problem was that you have other problems that develop as a result. His heart eventually gave out, and he died at a relatively young age. But that is the pituitary gland. It's the master gland and in charge of growth. The thyroid gland is located literally right by the neck. It's the one for our purposes. It helps us with metabolism, the maintaining of weight. How people can eat and the body just burns it off very quickly or doesn't burn it off very quickly. The thyroid plays a major part in that. It releases a hormone called thyroxine, which helps us with that metabolism. But that's what the thyroid does. Adrenal gland is located, and I know this, there's some parts here that are kind of a whole bunch of things here, but the adrenal glands located roughly in the stomach area, roughly. They would, again, not give you a chart and say, hey, what's this doing? Or what is this part supposed to do? Or what is the name of it, or where's the adrenal gland? But they, if you know roughly it's in the stomach area, it helps with a number of different things. But it helps us with emergency energy. When there's an emergency and our sympathetic nervous system kicks into high gear, the adrenal glands might release adrenaline or epinephrine into the system that will give us emergency energy. It will also help us with the metabolism of salt as well, kind of a minor point, but a point nevertheless. The pineal gland is part of the endocrine system that helps us with sleep. It helps us with our ability to fall asleep and wake up, releases a hormone called melatonin. Melatonin is what specifically helps us with the sleep cycle, the ability to fall asleep, the ability to wake up. Some people who are traveling across different time zones and might have jet lag might take melatonin to help them adjust their bodies to a new sleep cycle. The pancreas, located roughly again in the stomach area, is what helps us with sugar regulation, the ability to regulate sugar in our body, releases a hormone called insulin, which helps us regulate glucose or sugar. People with diabetes, there might be some type of issue with the pancreas where they're not releasing enough insulin to break down the sugar that's in the body, and the sugar levels can be out of balance, and that can cause problems. The gonads are also part of the endocrine system. These are your reproductive aspects, reproductive parts of the endocrine system. In the female sex, it's the ovaries, which release estrogen. In the male sex, it's the testes that release testosterone. It was once thought that females only released estrogen and males only released testosterone, but as it turns out, the ovaries do release very small amounts of testosterone, and the testes do also release small amounts of estrogen. And those hormones very important to both sexes. But for the female sex, estrogen is the primary hormone, whereas for the males, testosterone is the primary hormone. All right, so that's the endocrine system. And again, questions and then there's a bunch of questions that'll be answered towards the end. That's great. Any questions, please pose them in the question box. The EEG, also known as the electroencephalogram, you do not need to know what EEG stands for. You do not have to spell it. So long as you got EEG, that's all you need. The EEG is the part of the brain that measures brain waves. So here, if I'm seeing, what parts of the brain are active at a particular time. So beta waves are often what are found with being alert and awake. So if a person is doing exercise or working on a math problem, and we take a EEG reading of your brain, there's a lot of beta activity going on. Alpha is associated with being relaxed, but still awake. So you're not very active, you're not running, you're kind of just sitting there, relaxing a bit. Those are alpha waves that are going on, or predominantly going through your brain. Theta waves correspond to light sleep. Notice that as we go from beta to alpha to theta, the brain waves get fewer and they get bigger. And so what's happening there is that it's essentially the brain waves are slowing down, the brain activity is slowing down, not surprisingly, going from being very active to light sleep, and then finally in deep sleep, which is delta. In this case, this corresponds to deep sleep. There is gamma waves as well, but I do not think they're part of the AP curriculum. Gamma is one step above beta. It's like very, very strong hyperactivity of the brain. That's what gamma does. Okay, so given that, we're segueing here into stages of sleep. Different stages of sleep. Some textbooks still might teach 4 stages here. A lot of the newer textbooks talk about 3, and I will correspond or work on with 3 here. So in stage 1 sleep, a person still thinks they're awake. You're kind of lying in bed, your eyes are closed, you kind of still hear what's going on, maybe someone comes in and tries to talk to you and you try to respond, it's very mumbled. That's probably stage 1 sleep that you're actually in. You might get hypnic or myoclonic jerks where you're kind of laying in bed and your arm, your leg jerks or suddenly moves. That does happen in this stage. So I'll get to REM sleep in a little bit. I wouldn't quite necessarily say that it's similar to beta waves, but the question was, is REM sleep beta? I wouldn't quite go there per se, but it's very close to it. Also in stage 1 sleep, there is hypnic imagery, which is essentially, some people when they're falling asleep might start thinking they're dreaming. Really what's going on there is that your brain is becoming very active. It's starting to show some activity similar to dreaming, but not exactly the same thing. So hypnic imagery is going on there. It's kind of like hearing sounds or seeing sights, something like that. Stage 2 sleep, okay, notice just have some brain waves here. Two interesting looking things here. And again, I don't think they're going to give you brain waves and say, hey, what's going on here? This first part is called a sleep spindle. It's kind of a burst of activity that happens for maybe a second or two. It happens during stage 2 sleep. Does a person really experience anything? No, not really for our purposes, but that's what a sleep spindle is. A K cluster is usually 1 or 2 very big waves. You can see there's just that one big wave there, much bigger than any other wave there. Usually it corresponds to hearing a loud noise, or you're sleeping and there's suddenly this loud something or another, or maybe something touches you or rustles you or something like that. That would be essentially a K cluster that would happen there. That's the idea. So that's what causes the K cluster to occur. All right. So deep sleep is just that. It's deep sleep. The brain waves are much bigger. And all for that we're going to say is it's deep sleep. So are people not hearing me? There was something in the chat here. Are people not hearing me right now? Can you hear me right now? Okay, so it seems like my audio is going to, okay. So if you're having audio problems, obviously you won't be able to hear me right now, but again, just a reminder, this whole presentation will be available shortly after the presentation's over. So, all right, you can hear me now, great. So this whole, I'm just gonna type this out here, this whole presentation will be available later on, usually within an hour. That's the goal, unless Crowdcast has a problem again. So, all right. Does everyone reach stage 3? For our purposes, yeah. I mean, could there be some, speaking of sleep, so Scholar says, when's my son going to wake up? Don't jinx it. If he does wake up, I'm blaming you. So, well, so far he's doing well. I think he was cranky all day. Do some people reach stage 3 sleep? I think everyone reaches stage 3 sleep as far as we're concerned. Could there be some sleep disorders? I imagine there might be, but I couldn't tell you what they were offhand, and it's not my specialty. So REM sleep. So what happens during REM sleep? REM sleep. Rapid eye movement, that's where it's hard to do, but if your eyes were open, your eyes may be darting back and forth like this. I know maybe my picture's very small on your screen, but my eyes are going back and forth. If you close your eyes and you feel your eyelids as you do that, you'll kind of see this movement. That happens during REM. You're dreaming during REM. This is where dreaming occurs. And your brain is actually quite active, almost as active as if you're awake. Someone asked the question, like beta waves, alpha waves? Actually, I think it's closer to alpha than to beta, but again, it's not that terribly important in terms of that specificity there. But your brain is actually rather active. But on the other hand, and I apologize, I'll fix this when I upload these slides, there's no movement below the neck. Between neck down, there's actually no movement that is going on there. So that is, it's kind of called paradoxical sleep sometimes, because when you're dreaming, your brain and your brain's very active, your eyes are moving, you're actually breathing kind of heavily, but your muscle movements from the neck down aren't moving. Sometimes called REM paralysis or sleep paralysis. Some people have sleep paralysis. I'll talk a little about this later on. They wake up, they can't move their body. It's probably because part of their brain is still in REM. So, and sometimes they might use non-REM to refer to when you're not in REM. So stages 1, 2, and 3 are considered non-REM, and then REM sleep being different from non-REM. Again, I don't think this is too terribly important relative to what you might see here, what might be asked in the actual AP exam, but notice the difference between the different stages of sleep. Notice how the REM is very similar to kind of, I'd say, stage 1 light sleep in this case. So your brain's actually pretty active. It's actually fairly active. It's not deep asleep. A person says, gosh, I slept really deeply because I dreamt all night. Well, if you were dreaming, you weren't really sleeping deeply at that point. That's the idea. So when we talk about this REM versus non-REM stuff, a few comparisons here. Some of this we've touched upon already. First off, question is REM part stage 3 or after? So it's actually a hypothetical stage 4. In the old days, there was a stage 5, but it's a separate thing. You have stage 1, 2, and 3, and REM. So it's 4 stages total, although they're numbered 1 through 3, and then REM sleep. Categorize that in your memory as you want, but that's the idea. In the old days, there was stage 1, stage 2, stage 3, and stage 4, and then REM. But for our purposes, it's now stages 1, 2, 3, and REM. So REM is separate from it. So, all right. In non-REM, it's possible in so much as that person might move around a little bit in non-REM, or they might sleepwalk in non-REM. You can't sleepwalk while you're in REM. It is possible in non-REM, though. Dreaming is very rich in REM, and if there's any type of dreaming, it's not really a dream. It's maybe a flash of an image or something like that, and that's it. The timing of it gets longer as we sleep longer. The more we sleep, the more REM that we're going to be in, and it gets shorter. As we said, the more we sleep, the shorter that it gets. So to kind of look at this from this chart here, this actually uses the old 5-stage model here, and but still, for our purposes, call the stage 3 and 4. We combine them together. We start off stage 1, stage 2. We have some non-REM sleep going on, some deep sleep. But as the time goes on, we cycle back and forth between REM and non-REM. And as you can see, the REM cycles are getting longer, but the non-REM cycles are getting shorter. So towards the end, if you're sleeping 9, 10 hours a day, who sleeps that long? That'd be nice. You're going to be dreaming a lot more. So that's what happens there. As we age, you're sleeping or you're dreaming, or both. So this is your dream, and well, okay, you're dreaming about being in a Fiveable CRAM session. Hey, happy for you. So hope you're learning something in the process. So, all right. I'll just give you a very quick plug. My expertise actually is in hypnosis. I do hypnosis research, and in hypnosis is nothing like sleep. They took hypnosis out of the AP exam for this year, so I'm not even going to get into it. But after the AP exam is over, I might do a special presentation on hypnosis. No, you won't get hypnotized. No, I won't hypnotize you. Don't ask me. But that was something I have planned after the AP exam. So sorry to disappoint you, but if that is your biggest disappointment in life, then you are way ahead of the curve. So anyway, going back to this here, REM versus non-REM sleep, notice that the amount of REM sleep that goes on, we spend a lot of our time in REM, almost 50% of our time in REM, or of our sleep, I should say, when we're born, is in REM. And as time goes on, we spend less and less time in REM. Less of our sleep is REM, and less of a percentage of it is in REM. Let's see here. You're all about 14 to 18 years of age. According to this, you should be getting about 10 hours of sleep a night. Now, maybe if you're closed down or you're doing virtual learning, maybe that's possible, but I doubt that was happening. So, um, column one, I'm not sure what you're referring to in column one. I see. Yeah, I see what you're saying. I'm sorry. Um, column, what happened? Okay, that was I had to put that in there for this to work. So don't worry about column one. Just ignore that. So pretend that's not there. I should have somehow taken that out, but I couldn't. So, but all right. Anyway, um, about non-REM timing, it goes back to this. The more we sleep, the longer. This is one night of sleep. And as time goes on, we spend less time in REM. I'm sorry, we spend less time in non-REM. Wow. We spend less time in non-REM the longer we sleep. And by the late stages of sleep, we're doing a lot of it in REM, a lot more of it in REM than we do in non-REM. So, all right. If a person is not spending much time in REM, let's say they do a sleep study where you're about to enter REM and they wake you up, and so then let you go back to sleep, and they just don't allow you to have REM. What will happen is that they let you go back to sleep at night and uninterrupted, you're going to have a lot more REM all of a sudden. It's called the REM rebound effect. This is why sometimes people experience having very vivid dreams. Let's say they haven't slept for a couple of nights in a row. They were pulling up a whole bunch of all-nighters one after another, and then they go back to bed, and then suddenly they're just dreaming like crazy, in part because the body is trying to make up for the missed out REM. That's the idea. Kind of a REM rebound effect, it's called. So I miss out on REM, and then guess what? My body's going to make up for it later on. That's the REM rebound effect. Sleeping problems. Why is it we have trouble sleeping? Well, different types, I should say. One is insomnia, where it's the inability to fall or stay asleep. Narcolepsy is where a person is wide awake and then they might have what's called a sleep attack, where suddenly they go right into REM sleep. And because they go into REM sleep, their body from the neck down stops working, and they may actually collapse on the floor, called a cataplexy. They go right to REM sleep. They're not really dreaming, and it's not very refreshing sleep. It's not refreshing sleep. Let me be clear about that. People with severe narcolepsy are going to have difficulty sometimes staying awake. I have a friend who has narcolepsy. On the day of her wedding day, between the ceremony and the reception, it was like a 45-minute drive. She was sleeping on her husband's arms, just like in the limousine. She couldn't stay awake. Again, this is her wedding day. It should be very, very exciting. It should be she had difficulty staying awake. So that's narcolepsy. Sleep paralysis, on the other hand, is, I talked about this a little bit. A person wakes up, but they can't move. Their body, they can't move, and they might be like that for a couple minutes. It's because part of the brain is still in REM and they're having difficulty moving. That's what's happening there. Sleep apnea is a breathing difficulty that happens at night, where things like diabetes, obesity, a few other physical ailments can create the problems of sleep apnea. A person who snores a lot or snores very loudly might, I'm not a doctor here, not a medical doctor, so I'm not trying to diagnose anyone, but might have narcolepsy. It might be to a sleep study to have it checked out. It can be potentially deadly if it's severe, because the airway is not getting enough air, the blood's not very oxygenated, and that there are people who have died of complications of it. That's why they might have a CPAP machine, which is a device that basically forces air in the nose or into the lungs. And then somnambulism, which is a fancy word for sleepwalking. This happens during non-REM sleep, where a person is again, they're not dreaming. The brain is not very active enough to walk. They can get out of bed, and so have a good night, Jana. She's leaving for another CRAM session. Sorry that they're so back to back, or there's a conflict there. So, but again, this will be available after we're done. So, all right, have a good night. So that's somnambulism. Dreaming is why do we dream? Okay, or what are some theories of dreams or some elements of dreams? First off, when we talk about dreaming, have a good night. When we talk about dreaming, we have manifest content, which is what you're actually dreaming, and latent content, which is the hidden meaning of the dreams. This is very Freudian, by the way. Freud was very big into interpreting your dreams and saying, well, you dreamt about going on a cruise, but in real life, what the hidden meaning is, it's a representation of your journey in life or something like that. Sounds silly, but it is a psychodynamic approach or psychoanalytic approach. And by the way, don't bother buying those books in the bookstore about what your dreams mean because there's no evidence to back that up. So, all right, why do we dream? Freud suggested that we dream because it's a type of wish fulfillment. We dream in order to fulfill wishes. So, you take one look at me, you realize I'm not going to be pole vaulting 25 feet anytime soon. I don't even think I can make a pole big enough for my size. So instead, in order for me to experience that, I dream about pole vaulting 25 feet, which I think would crush the world record, as it were. But so I do that in order to fulfill a wish that I can't have in real life. Rosalind Cartwright suggested that dreams are a type of problem-solving mechanism, that I'm trying to solve an issue, and dreams allow me to work through a problem. The Hobson and McCarley model is sometimes referred to as the activation synthesis model. Think about all the activity that's going on in your brain, the stuff that you've seen, or experienced, memories, emotions, ideas, creative thoughts, and you're sleeping, it's just going through your brain right now, and suddenly it's like, wow, there's all this activity. Well, your brain perhaps takes it all and organizes it together, synthesizes it into this weird random thing called a dream. And it would explain why dreams are so make no sense, because it's all this randomness of your brain activity. I would say the one that makes the most sense for our purposes is activation synthesis model, although people have dreamt about things where they're fulfilling wishes that they couldn't have in real life, validating some of Freud's ideas. People have gotten insights and have solved problems with dreams, which validates Cartwright's theory. But I would say that the Hobson-McCarley best explains most people's dreams. So I'd say perhaps activation synthesis, but I don't think it's a question of who's right and who's wrong. Theories are theories, but that's probably the most probable. So distressing dreams, a nightmare versus a night terror, they are not the same thing. Nightmares happen during REM. Night terrors happen during non-REM. Content is very rich and detailed in a nightmare, but whereas in a night terror, there's very little of it, but it's quite intense. The duration is very long. A nightmare can be very long, whereas for a night terror, it's remarkably brief. And the movement, there's none from the neck down when you're having a nightmare, whereas a night terror, you could exist and you could wake up. So this idea that this person has this really long, vivid dream, seen in television all that, this long, vivid nightmare, and they're kicking and screaming and yelling, and that doesn't happen, because if they're having a very long, detailed dream, they're in REM and they're not moving from the neck down. Usually what happens when a person has a nightmare and they wake up and maybe you've had this experience where you're actually kind of tranquil. It's like, God, that was a really bad dream. But your body's very relaxed because, well, you were just in REM sleep and you weren't moving. But this idea of you're kicking or shoving, that happens during non-REM. It can't happen during REM. So that's the difference between a nightmare and a night terror. All right. So now I'm going to get to your questions. 16 questions, it looks like, have been asked here. So I'll just go in order that they appear. Let's see. In later CRAM sessions, are we going to be going over the FRQ types that College Board told us about last Friday? Yes. So there hasn't been a specific CRAM that has been designed for that yet. However, and there have been things in the past about the FRQs, and those streams on FRQs still are 98% valid today. The difference being the time's a little different and the emphasis is a little different. It's actually a pretty good idea. What I'll probably do is I'm going to ask Fiveable if there can be something like that. I would be happy to host something like that. So, and that would definitely be part of the. There will be some review at some point, but I think that's something that should be talked about sooner than later, personally. So I will post that. Maybe there has been something planned. I'm not sure. There are other people who do psych things too, though they're not with the CRAM. So, all right. Are terminal buttons and synaptic gaps the same thing? No, terminal buttons are at the end of the terminal branch. It's this little knob. And here's a synaptic cleft in front of me, and there's the next neuron in front of it. It's the little thing that will release the neurotransmitters into the synaptic cleft. So they're not the same thing there. So there's that. Are SSRIs considered agonists or antagonists? I never, well, I wouldn't even go to, I wouldn't consider it either, because an SSRI stands for selective serotonin reuptake inhibitor. And what it does is it goes into the synaptic, basically what it does is it goes to the neuron and it inhibits synapses that are in charge of serotonin. They don't let the reuptake happen. And so what happens here is there's more serotonin that kind of floats around that synaptic cleft, which will, in theory, fire off the happy neurons that serotonin are supposed to fire off. So I wouldn't call them either. It's more of, it's meant to create or to allow more serotonin to bind, but they're not agonists for serotonin. They're not really blocking a neurotransmitter. They're stopping the reuptake process. So that's what I would say for that. So migraines usually by high levels of glutamine. Yana or Jen, I'm not sure if that was which how you might which pronunciation you go by. High levels are correct. So okay. Reticular formation filters out. I would say it actually, I believe it sends it, it filters out afterwards. Again, I'm not exactly sure about that, but that's not a terribly important thing. But I'm pretty sure it happens afterwards, because the thalamus is the first part that kind of gets all that sensory information. So, difference between the old brain and new brain. So, old brain, you know, basically we can say we have three brains. So, the hindbrain, the midbrain, the forebrain. The hindbrain, the most basic brain, our primitive brain, is in charge of things like our ability to breathe and live. If you put the hypothalamus, it's part of that too. Our ability to eat, our ability to fight, or feed, to reproduce. All of those things are kind of part of that primitive brain. But then instead of updating the brain, they built on top of it. It's like taking a basic camera, and instead of upgrading the camera, you put fancier flash apparatus, a fancier lens, and that's kind of what it was like. So, yeah, no, that's basically the difference between the old and new brain in an evolutionary perspective. So, and Drew asked a question, and is it Akshita? Is that how you pronounce it? Answer the question. Yeah. So, okay, good. I'm glad I got it. So, all right. So, does the hippocampus work with the amygdala? Well, I mean, when you talk about memories, most memories have some emotional bits to them, I would suppose. It's almost like saying that a memory that may or may not, well, that might have some emotion to it or may process in different ways. So, it's not like they work hand in hand, but they do work together. I would say that, certainly. So, is the amygdala emotional in general or specifically aggression or fear? So I would say it's more, they say more the basic, more the primitive types of emotion, such as aggression and fear. However, for the AP exam, they tend to be a lot more liberal in what they accept, and I would say more of any type of emotion for our purposes. Is there a psychological difference between emotion and feeling? Not that I know of. Not that I am aware of. Just got a message from Fiveable. Okay, never else. So for our purpose, I say really not for our purposes. No. So, but take it for what it is. So I hope it makes your FRQ that much easier too. So, pneumonics for Broca's an area, for Wernicke's area. I don't. If anyone in the chat has a good, if anyone has a good mnemonic for Broca's and Wernicke's, I mean, I really don't have one, to be honest. I know there's some out there. Um, hmm, the way I remember Broca's and Wernicke's, it's so silly. First of all, for some reason I just remember because I had a relative who had Broca's aphasia and she had difficulty speaking. That's why I remembered it so easily. But in terms of location of the brain, it just went in alphabetical order. Okay, I'm looking at the left hemisphere, and Broca's was in front, and Wernicke's was in the back, and went in alphabetical order. That's all I can offer with you for that. But there are things out there, and if that is that a mnemonics video for Broca's and Wernicke's? Is that by chance? Oh gosh, Michael Britt's mnemonics video, where it's like a 17-minute long video where it talks about different parts of the brain. Okay, I should post that too if I think of it. It's a good. Okay, so yeah, if you want to use that, please do. So, does the thyroid control set point? Set point theory is technically not part of this unit, but this idea is that our body is set to be at a certain weight, and so if we eat more, our body will make us feel less hungry, and vice versa. I wouldn't say a control set point. If anything, if set point's real, I would say maybe the hypothalamus. But the hypothalamus would tell the thyroid, "Hey, up the metabolism or slow down the metabolism." But I wouldn't say it controls set point per se. So that's my answer for that. Is melatonin also a neurotransmitter? It might be, but I don't know for sure. A lot of them are kind of both. For our purposes, it is, we'll call it just a hormone for our purposes. Lucid dreaming. Well, what about lucid dreaming? Well, lucid dreaming is essentially, it's the experience that you are dreaming and you know you're dreaming. And you can control your dreams even. It depends. Some people can, some people can't. But in classic textbook definition, I can control my dreams. I can dream anything I want. So is there any specific mechanisms behind lucid dreaming that we would need to know here? I don't think so. So should we know all the neurotransmitters? The ones that I've talked about here are definite. They're fair game. If you look up all the possible neurotransmitters, you're going to see words that are really long and have lots of weird spellings. You don't have to get that specific. Serotonin, dopamine, GABA, the things like that you do need to know. What happens when you're interrupted during REM sleep? I did talk about that. The REM kind of rebounds. If you're on an EEG and you wake up a person and say, "What did you dream?" "Oh, I dreamt that." Well, basically, if you wake them up during REM, they'll tell you about a dream. Or if you ask them about, "Did you dream?" and say, "Yeah, I had a dream," because it's fresh in their memory. That's usually what happens there. 6 main ones. I mean, some textbooks talk about more. I'd have to really look at, but those are the big ones. Those are some of the big ones I talk about there. I would say if you stick to those 6, you should be good. But again, review your textbook, review it. But those 6 main ones are very good. Those are definitely ones you do need to know. Some textbooks will talk about other ones. The AP curriculum is a little vague in this respect, I have to admit. So, all right. How does the medulla play a role in sleep apnea? I would say because it controls breathing. I think that's maybe the medulla has to work a little extra hard, has to work harder, for it to for a person to breathe at night. That's my answer for that one there. So, and these slides will be available afterwards. Yes. So probably within an hour. Depends upon whether our Crowdcast is working for me. So, okay. All right. So that is a lot. I realize it's a lot of stuff. It was probably maybe about 3 weeks worth of material if you're on a regular 45-minute class schedule. That way I just went through. That's a lot of stuff to talk about in a little over an hour. Are there any additional questions I could answer? All right. Well, I'm not seeing any right now. So again, there will be. I hope you learned something. I hope I reinforced other answers some questions. I never think I do these well enough, and I'm glad that if you say I'm helping, I'm happy to hear that. So, the thing about this chapter, this unit, is it's a lot of memorization, just stuff. People get uh, very intimidated by the words, by the contents, this weird spellings of words. I'd say 80% of it's just memorizing vocabulary. What does this part of the brain do, or what does the myelin sheath do? So I think that's the important thing. So again, there are also, if you haven't if you haven't seen the practice prompts, they are available. There is two that have responses. I got to address or give feedback on those soon. But if you do those practice prompts, I will give feedback, especially for CRAM students. So that's important to know. So do we have to know the detailed procedure of the action potential? I mean, it can get pretty detailed. I mean, are there specific numbers they could ask? The answer is like specific parts. Multiple choice, the answer is yes, I would say. But again, the FRQ concept applications, I don't think that's going to happen. I could be wrong. So like I said, but I don't think they're going to say list the steps of the action potential. I just don't think that's going to happen. So, but I could be wrong. But I'd bank on that. So. No problem. So again, I hope to see you on future CRAMs. I'll be doing all the CRAMs, and I'll be doing Q&As as well. Theodore, my young son, just made a sound, so this might be serendipity in my queue that we've done it for now. So thank you very much for your questions. You have some great questions. Thank you for answering other people's questions in the process here. It's very helpful. I mean, this is crazy times we're living in, and this exam is just making it crazier, especially the way they're doing this. So hopefully we will get this. We're all going to get fives, all that good stuff. So have a great night, folks. Thank you again for your attention and your attentiveness. Take care.